The purpose of this video is to actually introduce you to simple dynamic system. Okay, simple dynamic system as shown over here. It's part of a control system that is being analyzed. So in our whole course, we will base on this system to do root locals and such. So this is the very basic. So if you don't understand this in the future, I don't think you may understand the other stuff quite clearly. Okay, so you may start by watching this video, or you can watch my video first and then you watch this video. Is intertwined, but nonetheless this is one of the very important videos because he actually talked about a lot of good concept. So you just type in this thing and you find this guy. And then let's start off with the key thing. So I will split this into 4 videos. Okay, maybe lesser. So the first part actually has to explain the physical system. Okay, that means I'm gonna explain this dotted box over here. Okay. So what does this actually mean? Okay. So this actually means is that okay, let's go term by term. Internal energy. The internal energy is the amount of stored energy, okay, that is within the system itself. The amount of change of stored energy, okay. And then A is the amount of power loss. And then the input power is actually UT. And this UT comes from a power output, maybe some motor or maybe some power output, I would say. So this power output itself consists of what? This power output consists of a controller and an actuator. So this portion here, in other words, this portion here is this thing. So they actually simplify this portion into one thing, calling it controller power output. But this controller power output consists of controller and a power output of actuator, you would say. So this straight box will actually eventually go here. So nonetheless, since this two can represent this one, so therefore this one can also straight away come here. So your power output of U of T also. So just to let you know, this can be rewritten as this. So this is the dt. Okay, it just pass into the summation. I hope you get what I mean. Okay, so you're just replacing power output as controller and actuator. In my, I just want to let you know. Okay, just let you know. And then without further ado, I'll just give you an analogy. So we have the internal energy as analogy. Okay, that is an analogy to saying that the amount of internal energy within the system at maybe certain time is this energy. Okay, so if I were to input some amount of water. Okay, input some amount. This is the input some amount of water into here. Okay, eventually you actually rise with the next time frame. Maybe this is time 1 second. So in the next time it will be 2 seconds, right? So there will be a change in the stored energy, which is also in other words internal energy. Okay, so there will be a change in internal energy as time passes by, and eventually you'll reach your desired output, YT. So I've made clear on this part, but however things aren't that nice. So let's say if you were to input the amount of water, but you expect this, let's say 1 second, to grow about 2 cm. However, within 1 second it actually grow about 1 cm in height. So you may find that there may be some losses. So the losses actually come from the leaks over here. So there are some leaking out. So there will be some power loss. Okay. So some power losses, some water loss, some energy losses. So the amount of losses plus the amount of rises, okay, the amount of rises will be equals to the amount of input at a particular time frame. Correct? So therefore, this explains this system. Okay. Nonetheless, I haven't finished yet. So there'll be a so-called summation point where you can actually see that how much the um how much the power loss are. And this is why, as I say, um at first, if you would expect, if there's no power loss, if there's no leaking, within 1 second you will rise 2 cm, right? But now we have only rise 1 cm, so you will typically think that, okay, the power losses is in terms of 1 cm of water, okay, that in height they're actually lost, they're actually being um they're lost, okay. So from here we can actually, from I, we can actually summation it, that saying that 1 cm is power loss. Okay, 1 cm is the change given into the water, that change the amount of the amount of height of the water itself. So I hope that I make this very clear. I really clear this part. Okay, so hold on a while. So from this equation over here, the amount of change in stored energy is actually the internal energy, as I say, while the power losses is this one, and the input power is this one, right? So the stored energy, we call it Y, okay, the amount of maybe the position, the height, position height, so maybe some position H, we call it Y in this case, so we just say that it's Y cm. So the change in Y over time is our change in stored energy plus our AY, because as we assume that, because you want it to be easier to calculate for the amount of losses, so we proportional it to YT so that we can calculate easier. So therefore AYT, okay, so the power loss proportion to the amount of output in this case. So in this case, these two add together will give you the amount of input. So it makes sense, right? The amount of input that goes into this system, some part of it will give rise to the height of the tank, part of it actually becomes losses. So if you sum up the losses and the part of it that give it a rise, will give you the input power, the amount of input power you have. So if you were to rearrange, so if you were to make it a Laplace transform, okay, you eventually get this system over here. And then you bring this s over a plus s plus a down here, you'll get a output. So y of s is output, u of s is input, multiplied by 1 over s plus a. This is g of s. This is a transfer function for only this system over here. Okay, so we simplify this relationship into 1 over s plus a. So 1 over s plus a multiplied by u of s. Okay, this is u of s. I mean u of t, but however, if you Laplace transform, you become u of s. Multiply by 1 over s plus a, you get y of s. So this is how it is being derived. Okay, and then hold on again. Now you may wonder, what is this open loop no measurement of yt? Now we are talking about open loop transfer function. Okay, this is simply the same as this. Okay, we have just derived this, just that the input u of s is equals to the amount of power losses. So there will be no change in stored energy in this case. Okay, so what does this mean? As we mentioned earlier, the amount of input will give rise to a change in the amount of stored energy. So it will give rise to the water level plus the amount of power losses. So when will power loss equals to input power? This is the thing that actually confused me a long time. So I realized that in order for power loss equals to input power, the amount of change in the stored energy should be 0. So when will it be 0 in this case? So for it to be 0, it should be at the brim, right? It should be at your desired output. So when your desired output is, when you're at the brim, your water is flowing out, there will be no change. There will be no change in the water level. Because the tank is full already, you cannot, there's no changes. There's no changes to your desired output anymore, because your desired output is equals to your input. Your desired output is already achieved. Your desired output is being achieved. So whatever flows out, okay, even this, that being the power losses flows out. This one flows out. Whatever thing that exceeds your desired output is considered also power loss, because you're wasting water. Okay, you're wasting the power. So all of this, including this, are all power losses. So in this case, the power loss is equals to the input power, and there is no changes in the tank, in the water level in the tank anymore, right? So therefore, it is, and so since the input power is equals to the power losses, whatever thing that flows out, we can say that the input U of S is equals to the output A over, A to the power of, A multiply Y over S. So this AY, okay, is actually the amount of power losses proportional to the level of Y, okay, proportional to the Y itself, the output. So therefore, as we say earlier, this is proportional to the output. So therefore, we also have to say that AY over, I think you get what I mean. So this is AY over S is equals, multiplied by 1 over S plus A. So this is still our transfer function. There's no change. Okay, this only change is just that AYS is equals to US. This is simply that. So you have this relationship. You know that this is equals to this under our condition saying that input power is equals to power loss, where there is no changes in the internal energy anymore. There is no changes in the internal energy anymore. You will have this scenario. So when you have this, you can actually do a partial fraction in order to solve for the answer, and this is the equation to describe the height and the time, okay, and also the graph itself for an open loop system. For an open loop system, assuming there's no measurement of YT. Okay, because when it flows out, you can't measure anything. And so this is just a one way system. There's no feedback system telling back the system that dude, things are overflow, stop the water level, there's nothing at all. So with this, I will end this video, and in the next video I will simplify this G of S. Since we know that this whole system can be called G of S, we will simplify this into a smaller version, like how we simplify this control power output as, from controller and actuator into this thing. So in the next video we'll just show you. So see you there.